let us start. Basically, Andre is running most of the talk. I just give him the introduction as usual. So just as a reminder, what we talked about since May or so about the NCHI ecosystem, where we have the NCHI in the center and we have the different layers all around. And those layers are set up in a way that you've got groups, like for example, our stereochemistry group, that are pretty near to the core of NCHI. And therefore, if you take any decisions over there, we have to see how the core is going to be developed. We have other parts like the mixture NCHI or the reaction NCHI that are just consumer of the NCHI because we are just using NCHIs to compile them, for example, to represent reactions or mixtures. And last but not least, we have areas that are working all around, from education to using QR codes to Resolver, which is a project to let you find any NCHIs out of an NCHI key. Yeah, so you may just remind this picture. How are things developed? We talked about that multiple times now. We've got multiple working groups. Again, we've got working groups that are near to the NCHI developments and other working groups that are all around, as just described. And today we are talking about the extended stereochemistry with the general introduction of stereochemistry and how stereochemistry is handled in the NCHI world. And with that, just the last reminder, that was our starting point for molecules. We had this nitro group, the way how the NCHI is set up. You see that we have got the general identifier for NCHI. 1S is the version number. Then we've got the molecular formula. We've got the connectivity table and the hydrogen layers. What is missing over here is the stereo layer. And that is what we're going to talk now. And now, Andre, I think it's your part.
First of all, about myself, I am chemist. Again, chemist by education, Moscow State University. I joined advanced chemistry development from the very beginning. It was about 26 years ago. And about 25 years, I'm dealing mostly with chemical nomenclature, algorithmic chemical nomenclature, name generation, and structure generation from names, and also dealing with chemical drawing software, ACD-Chem Sketch. ACD Labs is founded in Canada, and I work in Russian Development Office. So during this my work, I started to be involved with various structuring, coding, and representation things, tools, ways, and once again, probably from quite early stage when NCHI became iPad identifier, I was involved via several projects connected to polymers, some other things, and now I'm dealing with stereochemistry as soon as it connects in some way to nomenclature, as soon as nomenclature definition of stereochemistry is covered by, considered to be nomenclature specific, but those RS and ZE are too difficult and too inconvenient for algorithmic automatic generation. And NCHI provides very good and very quick, simple way to define, to record stereochemistry of your substance or simple structure via few layers. There are mostly 4 layers for stereochemistry. Layer reserved for double bonds, stereo, tetrahedral, stereo, B, T, M, and S layers shown in red. It is clever in that way that 2 enantiomers have almost exactly the same inches, only with different in M layer, M0, M1. Which is very good, it covers many things, still is very simple part. But unfortunately, there are areas still not covered recognized by NCHI. One of them is atrop isomers, mostly known for biphenyls, rotation isomers. Depending on substitution, they can exist as distinct substances and should be defined, but NCHI cannot recognize them, treating them as equivalent. Another area is that some areas of chemistry, for example, biochemistry, uses specific representation conventions for carbohydrates. In Hayer's presentation or chair representation shown in red and dark green here. And NCHI treats them in different way. NCHI cannot recognize them. And it is not so surprising. For example, as soon as one of the centers doesn't have any indication of configuration, you can see that that for center, number 5, according to carbohydrate numbering, it doesn't have any values, any stereo bonds. It is perspective drawing, and it needs some assumptions to get stereochemistry. Unfortunately, the same carbohydrate drawn here in 3 different ways will have 3 different inches. It is not convenient. And the last part that is important is NCHI does not support enhanced stereochemistry definition. So the ALPA project, NCHI project, was organized in September 19. You can see members. We have quite good representation of interested parties. You can see, for example, Cambridge Crystallographic Data Center, Sanofi Aventis, OpenAI. Now you can see that starting from the last version 106, NCHI can recognize specific cases, quite difficult for many software tools to recognize stereo, in this case, the Spire specific cases. You can see that version 106 cannot recognize such stereo. You can see that NCHI is the same, 2 enantiomers, and one has M1 and another M0. And in key, you can see that stereo is different second block. NCHI is clever in another way with NCHI key. As soon as in the first block you have connection information, and the second block encodes stereochemistry, isotopes, tautomers. So having NCHI, you cannot convert from NCHI key to structures since NCHI key is hash. But anyway, by the first block, you can find in the database all structures with the same connectivity, which is also convenient. And stereo is kept in second block. And this improvement allows to recognize stereochemistry in the bottom structure. It is more complex, but anyway, it works. Okay, this is some details about atrop isomers. What should be done and how NCHI can deal with it. The main problem is to recognize this specific bond around which you have hindered rotation. It is the most tricky part. But it can be defined and depends on available tools in NCHI. And the rest is very simple. You treat 4 substituents of this atrop isomeric bond, specific bond. You should treat it in the same way as allenes. You just need prioritize in equivalence, and that's all. And you can assign this layer. We have a document that describes how it can be done, and we need communication with developers to find ways how NCHI can cover them. So, carbohydrates. Here, it is not specifically NCHI part. It can be programmed inside NCHI or outside, but it looks like we need some procedure that will convert, will rearrange, will put some stereo bonds in these inconvenient representations to allow the standard NCHI procedures to treat these representations correctly. Currently, it is tricky when you have these representations. You can see examples. The first case of second block shown in blue is correct. It is the same as intended, as describes, as implied by this representation, but drawn in unambiguous. It is simple Greek pyramals. And you can get in some applications absolutely different stereochemistry for this representation depending on application you use. So we need these procedures, and it can be done. There are tools existing in some programs that can deal with this task. So we need to do maybe not so important, but biochemists prefer to use to operate with such representations, not the left one in blue that is totally unambiguous, indicates everything without any questions, but we need to think about it. Maybe not top priority, but better to implement. Currently, what NCHI can do is enhance chemistry. The procedures recognize the presence of these marks, but NCHI ignores them totally and generates only absolute representation. But via options, user can choose the way NCHI treats specific stereochemistry. For example, you can see NCHI options. User can choose absolute, relative, racemic, or from chiral flag. As soon as in MDL file, chiral flag indicates whether it is absolute or racemic configuration. Anyway, you can see that kinds of NCHIs you can get with specific options or chiral flag. Absolute has all layers specified here with M1, S1. Relative doesn't have M1 and indication S2 and racemic S3. It interprets these specifications as overall. All centers are treated in the same way, but it is not what we expect with enhanced stereo. I provide here this structure with 5 distinct stereo groups. The first one, absolute group, and in each numbering, atoms 3 and 5. We have one racemic group, or one that includes these 2 atoms, another racemic group with 1 atom in it, then again 2 atoms in the relative group, 2 atoms with dependent stereochemistry, and the last one, or 2, just 1 atom in each number, it is 4. What could be proposed format to include this information? It seems logical. We can discuss some small details. Do we use dash or parentheses or something? But we need to indicate kind of stereochemistry, absolute, and least atoms. Relative and least atoms. with separation of groups, as soon as 6 and 8 are dependent, you can change them, switch them, but both to opposite configurations. And independent group with one atom, you can switch one independently. So you can see groups, it is explanations, and we will need to adjust T and M layers. They are currently shown in gray. How we can solve this situation? One of solution can be just manipulation with this generated InChI, having information what atoms belong to what kind of group and what are dependent or independent. For example, I can spell what can be done. First of all, we need to minimize the generated InChI concerning only absolute group. As soon as these configurations cannot be changed, they are absolute. So we need to choose minimum, treating hyphens as similar. In this case, absolute group is atoms 3 and 5. You can see on blue. It is InChI numbering of atoms. We have T3 minus and 5 plus. We do not need to switch anything. So we freeze them. It stays 3 minus, 5 plus, and M0. If we need to switch, it will be 2 minus, and it can switch to M1. But in this case, no need to switch anything. Next, we go to enhanced groups. Simple. We treat them in increasing order of numbers as soon as they appear in this order in InChI. We have 4 plus. It is single independent atom of a relative group. We can safely change it to 4 minus. Next group of atoms starts with 6 and also it has dependent 8. It is already 6 minus, 8 minus. No need to change. Next group, it is a racemic group. Yes, and it has 7 plus, 9 minus. We need to change it to more preferred way. 7 minus, 9 plus. And the last atom, 10 plus. Change to 10 minus. And we have resulting, adjusted, minimized InChI encoding in high stereochemistry. That's all. This procedure, in this case, in quite complex case, works perfectly and it can be programmed by student for diploma work or even less. It is very simple. It is operation with text string with some knowledge of number atoms. That's all. But this procedure works smoothly only if we have unique atoms. If we have some structures when numbering depends on configurations, it can be more complex and needs tests. But generally, for most cases and correct application of enhanced stereo marks, it will work perfectly. What we have other, and we treat it as small but easy, small and easy tasks. Currently, InChI recognized stereochemistry in only short alleles with 2 double bonds and 3 double bonds. But in literature, we have a report on equivalence up to 9 double bonds. Should be very easy to expand in InChI, but it will demonstrate that InChI at least can encode these structures. And that's practically everything. What we already described, we have documents, we have ideas, should be discussed. details added, but anyway, main part is already done. It is enhanced stereochemistry, trop isomers longer allenes, and that specific tetrahedral case fixed in 106. Structure pre-processing model. We currently consider some additional modules a bit independent on NFDI4, and we already in NFDI4 discussions have tasks that can be resolved not involving main body of NFDI4 tools, but adding some preliminary treatment module like structure preprocessing, structure manipulation module. And here the task can be solved dealing with specific carbohydrate representations currently not convenient. Here we also put some tasks connected to organometallics, some specific changes in structures to allow current NFDI4 to treat them better. Main NFDI4 module tasks, most probably trop isomers and stereophylongarenes belongs to this part, and post-processing of NFDI4 strings. If we have difficulties to modify NFDI4 to recognize enhanced stereochemistry itself, we can add some very simple module that will modify the generated strings to include information about enhanced stereochemistry. That's all, and this is how I see how our group expects the progress with stereochemistry in NFDI4. And that's all from my part.
And the last slide is just the thanks we have to give around and to the groups and especially to Andre to work on that and to give us the specifics how the new stereochemistry is developed.